Okay, so thank you, Florian. Thank you for the invitation and the nice introduction. So I'm going to speak about cyclic Cramér-Rao bound under model misspecification. Actually, I thought that I'm going to be the only talk about model misspecification, but as we saw also, we have a few talks about this topic. This work is based also on the work of my student Malak Khatib. She is also here in the audience. And the outline of this talk is as follows. I will start with some background and motivation, then the problem formulation. I will present the misspecified Cramér-Rao bound, which is not a directional bound. And then I will present in the next part our work on the cyclic misspecified Cramér-Rao bound. This is our contribution here, an example and a conclusion. So I don't think that I need to convince the people here about the importance of directional statistics, but I will describe the specific problem that we consider here. We are speaking here about periodic, what we call periodic parameter estimation. So we have a parameter like an angle or frequency or phase or something like that, that it has some periodic nature. So in many practical parameter estimation problems, especially in signal processing, we have observation model, which is periodic with respect to the unknown parameters that we want to estimate. For example, in direction of arrival estimation in seismological data or radars and things like that. So here you can see a naive example of phase estimation. I have some observations of this phase and I want to estimate theta. Let's assume that I know the statistics of the noise, but this theta is between minus pi and pi, and the likelihood of this model is periodic. This is what we call periodic parameter estimation. And what I'm going to present here is what happens when the model is misspecified. For example, I assume some noise statistics, but this is not the true statistics. Okay, so again, I don't need to convince the audience here, but in periodic parameter estimation, traditional performance criteria like the mean squared error, this is the traditional performance measure in estimation theory, are inappropriate, and we need to replace them with the periodic cost function. So we can think about the modulo 2 pi estimation error here in this talk. Theta hat is our estimator and theta is the parameter that we want to estimate. So if I'm taking the modulo 2 pi of this estimation error and then the square, this is what we call periodic squared error. We can also take the cyclic error cost function, which is, you can see here, this is the difference between the estimation of cosine of theta. So this is the cosine of the estimator and cosine of the parameter to be estimated. And I'm taking the square plus the same for the sine. And here we have the illustration. Again, I don't need to convince you that if I'm trying to estimate theta and I have the estimator theta hat, then this red arrow, the squared arrow, is irrelevant, and I need to take the modulo 2 pi arrow here, the green, or the cyclic arrow. And in this talk, I'm going to concentrate on the cyclic arrow cost function. And this is because, as you can see here, the modulo 2 pi is not differentiable. It makes some complexity, so we are using this cyclic arrow. Now, if we look on in the history, what we have about periodic performance bounds, we can find bound on the mean cyclic error, again, the smooth periodic cost function, or on the mean square periodic error, the modulo 2 pi version. Okay, these are our two cost functions. We can find lower bounds that are Bayesian, meaning that we are trying to estimate a random parameter. We can find non-Bayesian or frequentist bounds when we are trying to estimate periodic parameter, which is a deterministic parameter. I think the earliest work is of Professor Mordia, and this is a Cramér-Rao type inequality. And after that, there are many others bounds, the Cramér-Rao bound, the Barankin bounds, here Ziv-Zakkai, and different bounds. But all these bounds are cyclic bounds, periodic bounds, but they belong to the directional statistical literature, but they do not account for model misspecifications. Okay, so there is no lower bound. In estimation theory, we are seeking over sometimes over upper bound, but in this context, we are seeking over lower bounds. There is no lower bound that accounts for both the periodicity and the model misspecification. If we look on the literature on model misspecification. So in this context, there are many works on how to deal with misspecified assumed model, because traditional estimation methods and performance bounds are based on the assumption that we have a perfectly knowledge or perfectly correctly specified model, but this assumption may not hold in practice. We have some misspecification. This can happen since we don't know the model, so we have some misspecification, but also because sometimes people take for simplicity, they take simpler model, and then they have some misspecification. So we have, I think we have some very early work, but if you look on White, I think this is what is relevant here. There is the analysis of the maximum likelihood estimator under misspecified model and its convergence. And if we look on, on the work of Wong, he developed the first misspecified Cramér-Rao bound, and there are many extensions in the last, let's say, 10 years in the field of, mostly published in the signal processing literature, about extensions of this misspecified Cramér-Rao bound. But again, and here you can see some model misspecification in the literature, and as you can see here, it's not just the Cramér-Rao lower bound, it's also for detection and for selective inference and for many other applications. And as you can see, most of this work are recent, not all. And but all this model misspecification works in estimation and detection theory do not take into account the periodicity or the directional statistics. So that's our goal. Our goal is to close this gap to develop performance bounds. In this context, what I'm going to present today is a Cramér-Rao lower bound that takes into account both the periodicity, so the directional statistics aspects, but also the model misspecification. Okay, so this is our motivation. Let's formulate it mathematically. So in estimation theory, we usually have observation vector x. It belongs to observation space omega x, okay? And here I have both two probability density function. Px is the true PDF, and from now on, I'm going to represent all the things that belong to the true one with the red color, okay, for simplicity. But my assumed probability density function is f. So in general, P and F are different. I have the true PDF, the ground truth, which is governed by the nature, and I have the assumed PDF, which is what I choose to do. And I'm designing my estimator based on this assumed PDF. What is nice is that because we are in directional statistics, we have here PDF that are periodic, both of them, both the true and the assumed, with respect to the unknown parameter. Okay, so I have this V here is the true unknown parameter, and theta is the unknown parameter under the assumed model. Okay. The work that we are going to see today is about non-Bayesian, so frequentist framework, and about periodic parameter estimation problem. So I'm going to use periodic estimation cost function, and we have periodic likelihood under both the true and the assumed. Okay, so the misspecification means that this F, the assumed PDF, is not necessarily the true PDF, the probability density function. Okay. So let's see what people did in the context of conventional statistics. So the first thing that Wong and others showed, White showed, is that the misspecified maximum likelihood estimator, this is the estimator that maximizes the assumed PDF, okay, which is not necessarily the true one. So this MMR estimator converges under some mild condition to what we call the pseudo-true parameter. This is theta star. What is this theta star? This is the parameter that minimizes the KLD, the Kullback-Leibler divergence between the true and the assumed PDF, which is, if you simplify the equations, then you can see that this is equivalent to maximization of this expectation. Again, the expectation is with respect to the true PDF. This is with the red color, P. And the internal term here is the log of the assumed PDF. So as you can see, the expectation is with respect to the true PDF, but the likelihood, the log likelihood here is with respect to the assumed PDF. Okay, so what I obtain is the pseudo-true parameter. Okay, so if you think about that, what I'm doing under this misspecified model, actually I'm estimating the pseudo-true parameter. I'm not going to estimate the true parameter because I don't know the true model. I'm not assuming that I know the true model. I'm going to estimate the pseudo-true parameter. That's what the maximum likelihood does, but also the other estimators. Okay, so then I need, in order to develop Cramér-Rao type bounds, I need some regularity conditions. I'm not going to go into details, but what you can see here is that I have regularity conditions that work both on F and on P, both on the true and the assumed PDF, okay? And then the bound that, again, this is the misspecified Cramér-Rao bound, and it was proposed by Wang a long time ago. As you can see here, I can see here the mean squared error, where here I have the estimator and the pseudo-true parameter, okay? The expectation is computed with respect to the true PDF. Because this is a bound, the performance bound can be based on the true PDF, okay, on the theoretical. And what you obtain here is a lower bound, which is function, if you recognize, you can recognize here the Fisher information terms. We have two different terms for the Fisher information. In conventional, correctly specified model, these two terms are equivalent. But here, because I'm using, here in the internal term, I'm using F, and the expectation is with respect to P, then this A term and B term are not identical in the general case. Okay? So I have here two information matrices, A and B, and that's what I get as the lower bound on the MSE. Again, this is existing results, well known in the literature. What I want to do here, I want to develop a lower bound on the mean cyclic error, on this function with the sine and the cosine. In order to do that, first I need to define what is the unbiasedness in our context. And what Lyman did a long time ago is define Lyman unbiasedness with respect to the cost function. So general estimator is Lyman unbiased estimator with respect to the cost function if the expected value of this cost function, when I compute it in a parameter, some parameter in the parameter space, will be larger than if I'm using the same, I'm computing the same expectation with the true theta. Okay, so my estimate of theta hat is the closest to the true theta. Okay, but this closeness is measured with respect to the cost function L, the specific cost function. And there are many examples to that. If you take the squared error cost function, then you will get the conventional, what we usually say, unbiased estimator is what we get here. But there are also many other definitions, unbiased test, unbiasedness on manifolds that Hendricks proposed, median unbiasedness, and some periodic unbiasedness, and there are many other examples that are based on this Lyman unbiased definition with different cost function. So our first step towards developing the new bound is to define this misspecified cyclic unbiasedness. And the idea is that we define that estimate of theta hat is a cyclic unbiasedness estimator under the misspecified model of the true pseudo-true parameter theta star. Again, I cannot guarantee that I'm estimating the true parameter because I don't know the true parameter. But the only thing that I can guarantee is that I'm estimating the pseudo-true parameter in the sense of the KLD, minimum of the KLD. So the conditions, the unbiasedness conditions here are these two conditions. The first one is that the expected value of the sign of the estimation error is 0. Again, the expectation is always with respect to the true PDF, but the estimation error is with respect to theta star, so with respect to the pseudo-true parameter. So how did I get this definition? I used Lyman unbiasedness definition, and I substitute this cyclic cost function. Okay, so I hope this is clear. I just took the Lyman unbiasedness definition. I took the cyclic cost function that you all know. So the estimation error of estimating cosine and the estimation error of estimating the sine. And then I get these two conditions. So this is the first step. The second step was to develop the bound. And again, Cramér-Rao lower bound is a lower bound on any unbiased estimator in the general case. In our case, we obtain a lower bound on the MCE, okay, the cyclic error, average cyclic error, evaluated at theta star, so at the pseudo-true parameter. And this is a lower bound on any misspecified cyclic unbiased estimator. Okay, so any estimator that satisfies these two conditions. Okay, and what you can see here is that the bound that I get is just a nonlinear transformation of the bound of Wong. Okay, so this is if I'm taking the misspecified Cramér-Rao bound, the MCRB of Wong, the conventional one, and doing this transformation, I'm getting the cyclic lower bound, our new lower bound. Okay, and just a quick illustration of the proof. Again, the mathematical details are not so important, just to see what are the ingredients of this proof. So we started with the Cauchy-Schwarz inequality together with our unbiasedness condition. Okay, so Cauchy-Schwarz together with the unbiasedness condition leads to what you see here. Okay, so this is the bound of the sine square, and here we have the cosine, and here this term. Then we use Wong theorem. This is the theorem that Wong used for the original misspecified Cramér-Rao bound. This is what you see here in the equation 4. When I'm substituting this equation in 3, I'm getting, and using this trigonometric identity, I'm getting the bound in 5. This is not the final bound, but if you are familiar with the inequality from Professor Mordia's book, not for the misspecified case, but for the correctly specified case, you can think about that as the extension of Mordia's inequality, but for the case of misspecification. Okay, so this is this equation. And then we apply the Jensen inequality, okay, to get the bound. So at the end, what is nice about this bound is that, as you can see, if you look on 5, you still have the estimator. So for any estimator, you will get a different bound. But if you look on 6, on the final bound, it is not a function, this, the right-hand side, is not a function of the estimator. So for any unbiased estimator in the Lyman sense, you will get the same bound. Okay? Properties of the new cyclic MCRB. So in the case of correctly specified model, our bound, the cyclic MCRB, coincides with the traditional cyclic MCRB. And the second proposition is that the cyclic MCRB is always lower than or equal to the conventional MCRB, which again makes sense because the circular cost function, the cyclic cost function, is always lower than the squared error. Let's see some simulation results. Florian, I hope I have time. So what we did, this is a collaboration with the industry, and this is a real problem that they brought to us. So in seismology, they have a array of sensors, and they have this model, and they want to estimate the direction of arrival. Okay, this is the DOA. But because they want to have a simple algorithm, so instead of using the true Gaussian noise, which is colored, which is full covariance matrix, they are assuming diagonal covariance matrix, just for simplicity, although they know that this is not true. So they want to see what happens. Okay.
1 minute remaining.
Okay. So I will just show the results. So let's see what happens under misspecification of, instead of taking the full covariance matrix, we are taking diagonal covariance matrix. Okay. And just the results, because I don't have time, but if you look here, you can see here the performance, the MCE, the mean cyclic error of the estimator, the maximum misspecified likelihood. This is the green line. And our bound is very tight bound. This is the blue line. Okay. The other elements are not so relevant. Again, I don't have much time, but you can see that the Cramér-Rao bound or the misspecified Cramér-Rao bound are not relevant bound. We need to take this, our bound, which is both take into account the periodicity, okay, that we work with the MCE and the misspecification. So to conclude, we consider an Bayesian or frequentist periodic estimation problem under modern misspecification. We first define the misspecified cyclic Lyman unbiasedness. Then we derive the new bound, the cyclic MCRB on the MCE, which provides a valid lower bound for periodic parameter estimation. we showed some properties, and we have now ongoing work on these directions. I think the most important one, which is related to the audience here, is that other directional statistics methods can gain from using misspecification. Again, we saw in Sophia's talk before me. And we have some publications. And I want to thank Malak and Nadav, my students, and Professor Joseph Tabrikian, Dr. Bert Horin, and Yael for working on this together with us on this topic.